Welcome back to LabRat Scientific. Now today I want to continue my series on rocket flight. I want to focus on guided rockets in this episode. Now I don't have millions of dollars to create a guided rocket to show you how they work, so I'm going to use some basic animations just to scratch the surface on the concept of guided rockets. Rockets are guided for various reasons. The two primary reasons are, number one, to compensate for wind effects and mechanical misalignments in order to get the rocket to land in the desired area, or, number two, to make the rocket fly to a desired orbit or point in space. There are many ways to maneuver a rocket. Here are three possible techniques. One way is to move the rocket nozzle. This is known as thrust vector control, or TVC. Two other techniques require aerodynamic forces. First, you can move the fins to change the direction of the rocket. Or you can add movable canards at the front of the rocket, and those canards move and change the direction of the rocket. Now, both of these aerodynamic techniques require atmosphere, unless they do not work in the vacuum of space. Let's focus on the thrust vector control method, or TVC. And to make my animation a little cleaner and to avoid any confusion, I'm going to remove the fins from my picture. This removes any implication of aerodynamic stability. Now, let's cut off the thrust for a moment. If you recall my lesson on rocket stability, you know that a finless rocket will tend to be unstable and will generally want to fly sideways. So here's my velocity vector, noted by the blue arrow. The unstable rocket will want to fly sideways. However, if I apply thrust and adjust my nozzle, I can create a moment around the center of gravity of the rocket, which pushes the nose back towards the velocity vector. Now, in a lot of cases, the rocket may overshoot, so I'll have to adjust my nozzle in the other direction to bring the nose back to the proper orientation. And the rocket might oscillate back and forth a little bit while I find the right attitude. Now, because the rocket is unstable, it will tip off, and I'll have to adjust the nozzle once again to be able to keep the nose aligned with the velocity vector. And this will continue on during all powered flight inside the atmosphere. Now, once the spacecraft leaves the atmosphere, we still need to control the attitude of the vehicle. Now, for satellites, this can be done in a number of ways. First of all, we could use cold gas thrusters. These thrusters do not produce flame, but they use highly pressurized gas being ejected out of a nozzle to control the satellite. We can also use reaction wheels, which are spinning disks, a lot like gyroscopes inside the spacecraft. As we speed up or slow down the wheels, the satellite will rotate. Or magnetic torque rods can be used. These rods utilize the Earth's magnetic field to be able to orient the satellite. Now, for human-occupied spacecraft, we can utilize cold gas thrusters, or also pyrotechnic thrusters, a lot like little rocket motors, to be able to control the spacecraft. Now here's a simple animation showing the pyrotechnic thrusters. Here's my spacecraft at one orientation. So I fire my thruster, and that begins to rotate the spacecraft. Now, if you recall Newton's laws, when I reduce the thrust or eliminate the thrust, the spacecraft will continue to rotate. I need to apply a force in the opposite direction to get the spacecraft to stop. Now, I come from the world of unmanned rockets, and we used cold gas thrusters to be able to reorient the payload once it's in space. Let's take a look at a quick video showing a cold gas thruster system at work. Here's a NASA video showing a sounding rocket main payload separating from a sub-payload. What you're going to see is the main payload moving away, but it's not spinning. And then you'll see the nitrogen gas escaping from the nozzles, causing the main payload to spin up. So let's take a look at the video and see what's happening. There's separation. It's non-spinning initially. Now we see the nitrogen gas reflecting the sunlight, causing the main payload to spin up. Now let's take a quick look at the components of a simplified guidance system. First, we need a flight computer to make the necessary computations and create the control signals that are fed to the nozzle or the movable fins. Now, we also need a bunch of sensors, such as a gyroscope, to measure the body attitude of the rocket. We also need accelerometers to be able to measure the X, Y, and Z acceleration. And quite possibly, we might have a GPS to determine the exact location of the rocket as it flies through the atmosphere. Now, the flight computer takes in the sensor data and computes the state vector of the rocket. The state vector is the rocket's pitch, roll, and yaw attitude, the rocket's acceleration and speed, and the rocket's position. The state vector is compared to what is desired, and the difference is known as the error signal. The flight computer then calculates how much the nozzle deflection is needed and the proper direction to drive the nozzles in order to reduce the error signals to zero. When the error signals become zero, the rocket is on the desired flight path. Well, now I realize that was a rather simplified overview of how guided rockets work, but hopefully it sparked some interest, so maybe you can do your own research to learn a little bit more about it. Now you can always go to LabRatScientific.com to get more information on rocket flight and space flight. Well, I hope to see you next time on LabRat Scientific.